In this topic, the properties and uses of conductors and insulators are described. A numerical example illustrating the impact of conductor resistance on a power system application is presented. In the first segment of this module, we saw how the application of an electromotive force, that is, voltage, forces free electrons to jump from atom to atom and so establish the flow of current through an electric circuit. In certain materials known as conductors, the movement of electrons from atom to atom is fairly easy to achieve, as the electrons are quite loosely bound to their respective atoms. These conductors exhibit a low electrical resistance and consequently allow a high current flow when voltage is applied. The best conductors are silver, copper, aluminum, zinc, brass, and iron. Wires which are used to connect electrical circuits are usually made of copper or aluminum, as silver is far too expensive. Certain other materials exhibit just the opposite characteristic to conductors. That is, the electrons are closely bound to their respective atoms, and therefore a much greater force, that is, voltage, is required to establish an electron flow. The class of materials is known as insulators and includes such materials as dry air, glass, rubber, mica, and plastic. Whereas the conductors are used to connect the actual circuit components and allow the passage of electric current, the insulators are used to confine the flow of electricity to the desired path and so provide protection. A typical application of this principle is shown here. We need to supply electricity to the motor-driven fan that is hung from the ceiling. Two conductors are run from the fuse box through a switch, then in conduit inside the wall up to the ceiling for connection to the fan motor. So we can see how the conductors are providing a path for electricity from the power supply to the fan motor. However, if the two conductors were allowed to come into contact with each other, the fuse would blow, of course. In order to prevent such contact, the two wires are both insulated, usually with rubber or plastic, to eliminate the possibility of electrical contact, thus confining the path of electricity and providing protection. Let's look at a numerical example. In this case, we have a single-phase overhead distribution line supplying power to a rural load, say a farm. The nominal voltage at the customer service entrance is 120 volts, and the load resistance is equal to 2 ohms. Thus, the magnitude of current passing through the line is 120 volts divided by 2 ohms equals 60 amps. Let's now consider the effect of conductor resistances, 0.5 ohms total in this case. As the load current of 60 amps flows through the conductor resistance, it will cause a voltage drop along the line between source and point of load. The value of voltage drop will be equal to I times R. 60 amps times 0.5 ohms equals 30 volts. Thus, in order to provide 120 volts at the customer's entrance, the supply company must maintain 150 volts at the source. Another problem of conductor resistance is power loss due to heat dissipation from the conductors themselves. This can be calculated from the expression power loss equals I squared R. In our example, this comes to 60 squared times 0.5 ohms equals 3,600 times 0.5 equals 1,800 watts or 1.8 kilowatts. That is a loss of 1.8 kilowatt hours per hour. So we can see that there are some penalties involved with conductor resistance, even though that value of resistance is very low when compared with insulators.